In this video, we're going to look at colored complexes, and we'll find out why transition metal ions form colored complexes, and we'll look at how different factors can affect the color of a complex. So when light passes through a solution that has a transition metal ion, some of the light will be absorbed and some of the light will be transmitted or passed through. If we take a look at the copper 2 sulfate solution, the hexa aqua copper 2 plus ions will absorb red and yellow wavelengths, which will make the solution appear blue, as you can see in this image. So there's something called a ligand exchange. So if I added some ammonia to a copper 2 sulfate solution, some of the water ligands will be replaced with ammonia ligands, and that complex is now a darker blue because it will start absorbing shorter wavelengths of light, so it will start absorbing yellows and greens as well, which will now make the solution appear more dark blue. So we can predict the absorbed wavelength if we know what the transmitted wavelengths are. So the transmitted wavelengths are complementary to the absorbed wavelength. So if a solution is blue, the wavelength that's being absorbed would be orange. So it would be absorbing light in the 585 to 647 nanometer range, and blue would be transmitted, so it's transmitting in the 424 to 491 nanometer range. Just remember that the color wheel is found in section 17 of the data booklet for your reference. There are a couple of exceptions where there isn't a colored complex. So solutions that contain copper 1 plus and scandium 3 plus are colorless because their D level is either full or completely empty. So in the example of copper 1 plus, the D level is full, and in scandium 3 plus, it's empty. So there's a phenomenon called D level splitting. So the D level orbitals in a transition metal, atom, or ion have the same energy, so they're said to be degenerate. However, when the atom or ion forms a complex with a ligand, the electrons in the ligands and the d orbitals will repel each other, and that will split them into orbitals of two different energies, and these are called now non-degenerates. So in this example, these two electrons split to a higher energy level than the ones that are paired. So for example, when electrons in the lower D level absorb energy, they'll jump up and transition to the higher D level, and this is called a DD transition. And the wavelength that is absorbed is the wavelength that's complementary to the color that's being transmitted, and the energy can be calculated using E equals Planck's constant times the frequency of light. So you can see this here. So we have our degenerate 3D orbitals. Some are up here and some of them are down here. And then there's been some energy absorbed from the spectrum that corresponds to that change in energy. So it jumps to the higher energy level, and then the electrons transfer up to the higher D level, and we can calculate that difference using the E equals Planck's constant times the frequency. So now we'll talk about the spectrochemical series. So the energy difference between the D levels is impacted by the ligands that are surrounding the metal ion. And the spectrochemical series will show the trend of D level splitting. So ligands that are higher up or have a greater ability to cause splitting than those that are lower down. So they also will displace weaker ligands in a complex, changing the color of the solution, which then explains that first example we talked about where the hydrated copper 2 plus ion was a nice lighter blue, but if you replace some of the water ligands with ammonia, it switched to a darker blue because these were able to bump out some of the water ligands and replace them. So you ended up with a darker blue solution. So the factors that affect D-level splitting are the ligand that surrounds the metal ion. So that's connected to the spectrochemical series. So you can see that. The second thing is the metal ion. So the different number of electrons in the D level will impact the D level splitting. The shape of the complex, so that will affect the repulsion between the ligands and the D level electrons. And then finally, the oxidation state of the metal ion. So the iron 2 plus and the iron 3 plus are different colors, for example. So the example we talked about before, so a solution that has the hexa aqua copper 2 plus ions is a lighter blue, and a solution with some of those water ligands replaced with ammonia is a darker blue. So you can see the left and the right are the lighter blue and the darker blue. And the reason why is the ammonia ligands lead to a greater splitting of the d orbitals because they are higher up on the spectrochemical series. And this changes the energy and increases it. And so a greater amount of energy is absorbed when the electrons transition to that higher set of d orbitals. And that will lead to a shorter wavelength of light being absorbed, and the solution will appear to be a darker blue color.